everyone. In this lecture, I'll be explaining certain symmetry conditions which will be helpful when we are evaluating the continuous time Fourier series of a function x of t. Suppose that is, we'll be discussing mainly three cases. First one, when x of t is an even signal, when x of t is an odd signal, and the last one when x of t or the signal is exhibiting half-wave symmetry. First, we'll consider when the given signal x of t is an even signal, that is x of t is equal to x of minus t. We know that is the definition of an even signal. Here they have given a simple example. Suppose x of t is a function given by 2 plus t square plus t raised to 4, and x of minus t, it is also the same function. It is obtained by replacing every t in the expression of x of t by minus t, and such functions are known as even function. And when x of t is an even function, we can find that certain the Fourier series coefficient a0, an and bn, they are having some coefficients become 0. So if you know this property beforehand, while doing problems, you don't have to evaluate the entire you don't have to do the entire integration and find finally the answer as 0. You can directly write, because of this property, symmetry property, that is, since the signal is even, so and so coefficients are zeros. Okay, so these are certain examples of even signal. If you consider this, we can see that here x of t is same as x of minus t for all these four signals. Okay, now in this case, we know the Fourier series coefficients are given by when x of t is an even signal. The Fourier series coefficient is a0 is 2 by t integral 0 to t by 2 x of t dt. Original a0 value is 1 by t integral 0 to t x of t dt. So there is a slight difference in the equation when we consider an even signal. Similarly, an expression is going to be 4 by t integral 0 to t by 2 x of t into cos n omega 0 t dt, and bn value is 0 for an even signal. Sometimes this is asked as question itself, that is, you will be asked to derive the Fourier series coefficients, or you will be asked to prove that when x of t is an even signal, the Fourier series coefficients are these. Okay, so we'll consider, next we'll see the proof of this derivation. In this a0, the original equation is a0 is equal to 1 by t integral 0 to t, that is, we are integrating the original signal x of t over one complete cycle. And also, if you consider the limits in this case, the limit of integration is taken from minus t by 2 to t by 2, so that we'll get that final result. Here also, this is one complete cycle, t by 2 minus t by 2 will give you t. So the integration is done for one complete period. And this limit of integration, now we are going to split this integration into two different integration, that is, the limit from minus t by 2 to 0, and the second is from 0 to t by 2, the two limits of integration. And in the first case, it is 1 by t into integration 0 to t by 2 x of minus t dt. Now how we are getting this? I'll explain that. What we are doing is, we are doing a change of variable. Consider this case, integral minus t by 2 to 0 x of t dt. Now I am substituting another variable. Let z is equal to minus t. Therefore dz is minus dt. That is, I am going to change the variable in this integration. Now integration is done with respect to the variable t. I am substituting a new variable. Let z is equal to minus t. Therefore what is t? Then t will be minus z, and dz is minus dt. Therefore dt is minus dz. Now here the lower limit of integration is minus t by 2. So when t is minus t by 2, what is z value? Z value is minus of minus t by 2, and that is t by 2. And when t is 0, the upper limit, z value is 0. Therefore the new integration in terms of variable z is going to be, the lower limit is, we got it as t by 2, upper limit is 0, and x of t is equal to minus z. Therefore x of minus z, and what is dt? Dt is minus dz. dz, and that negative side we have taken outside. Okay, and here you can observe the limit of integration is from t by 2 to 0. Okay, so we can change the limits of integration by putting a minus sign. So at this minus sign I am taking inside and I am changing the limit of integration to, or I can say I am reversing the limits of integration. It is 0 to t by 2 now, x of minus z into dz. Okay, now this is simply a variable. So finally we can change this variable z back to t. Therefore the final is integral 0 to t by 2 x of minus t dt. Clear? So what we have started with is integral minus t by 2 to 0 x of t dt, and we have obtained it that is to be equal to integral 0 to t by 2 x of minus t dt. Okay, so that is substituted here. That is how they have obtained 1 by t into integral 0 to t by 2 x of minus t dt plus integral 0 to t by 2 x of t dt. Now we know the signal x of t is an even signal. Therefore, x of t is equal to x of minus t. So replacing the x of minus t in the first integration by x of t. Now consider these integration. That is, both terms are same. Integral 0 to t by 2 x of t dt. So it can be written as 2 into. So it becomes a0 is equal to 2 by t integral 0 to t by 2 x of t dt. So this is how we have obtained the coefficient a0 for an even signal. Now we'll consider how we can derive the expression for an when x of t is an even signal. The expression for an is 2 by t integral minus t by 2 to t by 2 x of t dt, x of t into cos n omega 0 t dt. Here again see the change. The change of limits of integration is changed from 0 to t. Originally in the expression of an it is 0 to t. Here we have changed it to minus t by 2 to t by 2. Okay. So that is equal to 2 by t into this limits of integration we are dividing into 2. Minus t by 2 to 0, the first case, x of t cos n omega 0 t dt plus integral 0 to t by 2 x of t cos n omega 0 t dt. And here again we are doing the change in variable. X of t is replaced with another variable, let it be minus z as I have explained in the previous case. And finally when we apply the limit change in limits, we'll be getting an expression in this form, integral 0 to t by 2 x of minus t cos minus n omega 0 t dt. Here I am not giving the explained proof. You can try it by yourself in the same way as I've explained when we have derived the coefficient a0. In that same manner you can derive this also. Okay, and we know x of minus t is equal to x of t. Since this x of t is an even signal, also we know cos of minus theta is cos theta itself. Therefore within the bracket we are now left with two different integration, and both are the same, integral 0 to t by 2 x of t into cos n omega 0 t dt. Therefore it can be written as twice. So it becomes 2 into 2 by t is 4 by t integral 0 to t by 2 x of t cos n omega 0 t dt. And that is the expression for an. Therefore when x of t is an even signal, we have the expression for a0 and an. Now we will see what is going to be the value of bn when x of t is an even signal. The equation for bn is 2 by 2 and the limits of integration is changed to minus t by 2 to t by 2 x of t into sin n omega 0 t dt. And this limit is again divided into 2, minus t by 2 to 0, and the second case is 0 to t by 2. And again for the first case, that is minus t by 2 to 0, we are applying change in variable, and by doing so we have got the limits now extending from 0 to t by 2 x of minus t sine minus n omega 0 t dt plus the second term, it is remaining the same. So integral 0 to t by 2 x of t sine n omega 0 t dt. And here if you consider the first integration, now we can apply replace x of minus t with x of t since it is an even signal. Also we know sine minus theta is minus sine theta. Therefore, this equation becomes 2 by bn is equal to 2. Here bn expression is 2 by 2 into within bracket minus integral 0 to t by 2 x of t sine n omega 0 t dt plus integral 0 to t by 2 x of t sine n omega 0 t dt, and we can see that the terms within the bracket are same and opposite of opposite sign. Therefore bn value is 0. So we have when x of t is an even signal, the bn coefficient value is 0 and only a0 and an is having value. So if we know this property and if you are asked to evaluate x of t, which is an even signal, you don't have to evaluate the entire bn, write the equation of bn and do the complete integration. You can directly write for an even signal bn value is 0. Next case is when x of t is an odd signal, that is x of t is equal to minus of x of minus t. Here they have given a simple example. Here few signals are given which is odd, the signals are odd signal x of t, and when x of t is an odd signal, a0 and an both are 0 and bn is 4 by t integral 0 to t by 2 x of t sine n omega 0 t dt. This can also be derived in a similar manner when we have derived the even signal case. Okay, so first case is a0 is 1 by t integral minus t by 2 to t by 2 x of t dt. The limit of integration is changed from 0 to t to minus t by 2 to t by 2, and again the limit of integration is divided into 2, that is first is from minus t by 2 to 0 x of t dt, second is from 0 to t by 2 x of t dt. Again we are applying the change in variable for the first case, and when we do the change in variable as we have done for the even signal case, we will be getting this expression, that is a0 equal to 1 by t into integral 0 to t by 2 x of minus t dt plus integral 0 to t by 2 x of t dt. And we know for when x of t is odd, x of t is minus x of minus t, that is x of minus t can be replaced with minus x of t. Therefore a0 value is obtained as 0. Then in a similar manner we can derive the expression for an. An is 2 by t integral minus t by 2 to t by 2 x of t cos n omega 0 t dt, and the limit of integration is divided into 2, minus t by 2 to 0 and 0 to t by 2, and the first case the limit minus t by 2 to 0, again we have to do a change in variable. So the limit of integration is changed to integral 0 to t by 2 x of minus t into cos minus n omega 0 t dt plus the second term integral 0 to t by 2 x of t cos n omega 0 t dt. Now here x of minus t, since it is an odd signal, is minus x of t, and cos minus theta is cos theta itself. Therefore in the next step what we are getting is an as 2 by t within bracket minus of integral 0 to t by 2 x of t cos n omega 0 t dt plus integral 0 to t by 2 x of t cos n omega 0 t dt, which is equal to 0. Therefore if the given signal is an odd signal, the coefficient a0 and an values are both 0. Bn value we'll see in the next lecture, how to evaluate bn for an odd signal. Thank you.